There's something waiting for you at light speed, something physics has been hiding from you. Brutal acceleration in a spacecraft, stars turning into beams, time bending. You achieved the impossible, the speed of light itself. The next moment, it will rewrite everything you think you understand about how the universe works. And here is a question for you. If you could travel at light speed, where in the universe would you go first? Let me know in the comments. I'll pin the most creative answer. Now let's begin. Imagine you're traveling at 90% the speed of light. Time for you would pass at less than half the rate it does for someone on Earth. If you traveled for what felt like 1 year to you, more than 2 years would have passed back home. Push your speed to 99% of light speed, and 1 year for you equals more than 7 years on Earth. But here's the truly mind-bending part. If you somehow reached exactly the speed of light, which, spoiler alert, you can't, time would stop completely from an outside observer's perspective. Not slow down, stop. You'd be frozen in a single eternal moment while the rest of the universe aged around you. From your perspective, though, the journey would be instantaneous. You'd arrive at your destination the very moment you left. Distance would collapse to zero. Before we go further, if you're enjoying this deep dive into the cosmos, hit that subscribe button and give this video a thumbs up. Your support helps me bring you more mind-expanding content about our incredible universe. This brings us to another bizarre consequence: length contraction. As you approach light speed, distances in the direction you're traveling literally shrink. Not just appear to shrink, they actually contract from your frame of reference. If you were racing toward a distant star, 10 light-years away at 99.9% the speed of light, that distance would compress to less than half a light-year from your perspective. At the speed of light itself, all distances in your direction of travel would shrink to zero. The entire universe ahead of you would collapse into a single point. You could, theoretically, cross the entire observable universe in an instant, from your point of view, at least. Meanwhile, billions of years would pass for the rest of the cosmos. But there's a problem. A massive, insurmountable problem. You can't actually reach light speed, not if you have mass. And here's why. According to Einstein's equations, as an object with mass accelerates closer and closer to light speed, something peculiar happens to its mass. It increases. The faster you go, the more massive you become. And the more massive you become, the more energy you need to accelerate further. It's a vicious cycle that leads to an impossible conclusion. At 99% light speed, your mass would be roughly 7 times greater than your rest mass, the mass you have when standing still. At 99.9%, you'd be over 22 times more massive. At 99.99%, over 70 times more massive. As you push closer and closer to the speed of light, your mass approaches infinity. And to accelerate something with infinite mass would require infinite energy. The entire energy output of every star in the observable universe wouldn't be enough. You'd need more energy than exists in all of reality. It's not a technological limitation, it's a fundamental law of physics. This is why only massless particles can travel at light speed. Photons, particles of light, have no rest mass. They're born traveling at light speed and can never slow down. From the moment they're created, whether in the heart of a star or in the glow of your phone screen, they race through space at exactly 299,792,458 meters per second. They can't go faster, they can't go slower, that's their only speed. And from a photon's perspective, if we can even call it that, the concept of time doesn't exist. A photon emitted from a distant quasar 13 billion years ago doesn't experience the passage of those 13 billion years. From its frame of reference, it's created and absorbed in the same instant. The entire journey, spanning billions of light years and billions of years, happens in zero time. Think about that for a moment. Light from the oldest stars in the universe has been traveling through space for over 13 billion years from our perspective. But from the light's perspective, no time has passed at all. It exists in an eternal now, frozen between the moment of creation and the moment of absorption. Now let's talk about what you'd actually see if you were somehow accelerating toward light speed. The view would be absolutely spectacular and deeply strange. Due to something called relativistic beaming and the Doppler effect, the stars ahead of you would appear to shift toward blue light. The faster you go, the more extreme this blue shift becomes. Meanwhile, stars behind you would redshift, their light stretched toward longer wavelengths. At extreme velocities, stars directly ahead would appear incredibly bright and concentrated in a shrinking circle in front of you, while the space around you would seem to stretch and distort. The familiar constellations would be unrecognizable, twisted and warped by your incredible velocity. There's also something called the headlight effect. Just as a car's headlights appear brighter when it's moving toward you, starlight would appear more intense and concentrated in the direction you're traveling. The universe ahead would glow with increasing brilliance, while the cosmos behind you dimmed into darkness. But let's get practical for a second. How close have we actually come to light speed? Our fastest spacecraft, NASA's Parker Solar Probe, recently set a record on December 24, 2024. It screamed past the Sun at 430,000 miles per hour. That's 692,000 kilometers per hour. That sounds incredibly fast, right? And it is. It's the fastest human-made object ever created, but compared to light speed, it's crawling. The Parker Solar Probe is traveling at roughly 0.064% the speed of light, not 64%, 0.064%. It would take that spacecraft over 6,000 years to reach the nearest star system, Alpha Centauri, which is only about 4.4 light-years away. By the way, if you're curious about the challenges of interstellar travel, I made a video called "How Long Would It Take Us to Leave the Milky Way?", where I explored just how vast the distances between stars really are and what it would take for humanity to become a truly interstellar species. You should definitely check that out after this video. The video is in the description and on the card above. The Parker Solar Probe achieved its record-breaking speed using gravity assists from Venus, essentially slingshotting around the planet to steal some of its orbital energy. It's a brilliant technique, but even after multiple Venus flybys and diving closer to the Sun than any spacecraft in history, it's still moving at less than 1/10 of 1% of light speed. To put this in perspective, light can travel from Earth to the Moon in about 1.3 seconds. The Parker Solar Probe, our fastest spacecraft, would take over 5 hours to make that same journey. Light can circle Earth's equator 7.5 times in 1 second. The Parker Solar Probe would take over 6 minutes to go around once. The energy requirements to accelerate even a small spacecraft to a meaningful fraction of light speed are staggering. Let's say we wanted to send a probe weighing just 1,000 kilograms, about the mass of a small car, to 10% the speed of light. The kinetic energy required would be roughly 4.5 times 10 to the 17th joules. That's 450,000 trillion joules. To put that in context, the entire United States uses about 4 times 10 to the 19 joules of energy per year. So accelerating our 1,000 kilogram probe to just 10% light speed would require more than 1% of America's total annual energy consumption. And that's just to get to 10%. Remember what happens as you approach higher percentages. The energy requirements don't just increase, they skyrocket exponentially. At 50% light speed, the energy needed jumps to about 1.5 times 10 to the 18th joules. At 90%, it's about 6.5 times 10 to the 18 joules. At 99%, you're looking at around 3.5 times 10 to the 19 joules, nearly equal to the entire annual energy consumption of the United States, just to accelerate one small probe, and that's just the kinetic energy. We haven't even talked about the inefficiencies of real propulsion systems, the mass of the fuel you'd need to carry, or the energy required to accelerate that fuel along with your payload. When you factor in realistic rocket equation constraints, the numbers become even more absurd. This is why concepts like antimatter propulsion and fusion rockets are so appealing to scientists thinking about interstellar travel. Matter-antimatter annihilation converts mass directly into energy with 100% efficiency, following Einstein's famous equation E equals mc squared. If we could harness antimatter safely, which is a massive if, it would be the most energy-dense fuel imaginable, but even with perfect antimatter engines, you'd still run into the mass problem. To reach 99% light speed, you'd need to carry an enormous amount of fuel. And that fuel has mass, which means you need even more fuel to accelerate it, which adds more mass, which requires even more fuel. It's an exponential nightmare that quickly becomes impractical. The Tsiolkovsky rocket equation governs this relationship, and it's brutally unforgiving. Even with antimatter propulsion, the best theoretically possible chemical rocket fuel, getting a meaningful payload to a significant fraction of light speed would require a spacecraft where the fuel mass dwarfs the payload mass by factors of hundreds or even thousands. Some researchers have proposed alternatives. Project Breakthrough, Starshot, announced in 2016, envisions using powerful Earth-based lasers to push tiny spacecraft, essentially computer chips with light sails, to 20% light speed. The idea is clever: keep the energy source on Earth where we don't have to worry about its mass, and use focused laser light to accelerate ultra-lightweight probes. These spacecraft would weigh just a few grams each. They'd carry no fuel, no engines, just a reflective sail catching photons from an array of ground-based lasers. If the technology works, they could reach Alpha Centauri in about 20 years. It's an ambitious project, and there are enormous engineering challenges to overcome, but at least the physics is sound. Still, even 20% light speed is nowhere near actually reaching the speed of light itself. And that brings us back to the fundamental question: what would actually happen if somehow, impossibly, you did reach light speed? From a physics standpoint, the answer is clear: you can't. The equations break down, your mass becomes infinite, time stops, distances collapse to zero. The universe as you know it ceases to make sense. It's not just impractical, it's mathematically forbidden for anything with mass. But let's indulge in a thought experiment. Imagine just for a moment that the laws of physics took a coffee break and allowed you to hit light speed. What would you experience? First, causality itself would start to behave strangely. In our normal experience, cause always precedes effect. You flip a switch, and then the light turns on. You throw a ball, and then it flies through the air. But at light speed, the relationship between cause and effect becomes ambiguous. From certain reference frames, events could appear to happen in reverse order or simultaneously. This isn't just weird, it's fundamentally incompatible with how we understand reality. If you could travel faster than light, even hypothetically, you could theoretically send information backward in time. You could create paradoxes where effects precede their causes. This is one reason why the speed of light isn't just a speed limit. It's a fundamental feature of causality itself. It ensures that the universe makes logical sense, that causes led to effects in a consistent way, and that the past, present, and future maintain their meaningful distinctions. Then there's the problem of acceleration. Even if you could magically reach light speed instantaneously, the acceleration would obliterate you. The human body can withstand maybe 9 or 10 times Earth's gravity for brief periods before losing consciousness. Fighter pilots experience this during high-G maneuvers. To accelerate to light speed in, say, 1 year at a constant rate would subject you to about 0.97 times Earth's gravity. Totally comfortable, actually. But to reach light speed in 1 second, you'd experience an acceleration of about 30 million times Earth's gravity. You wouldn't just be crushed. Your atoms would be torn apart. You'd be reduced to a smear of subatomic particles before you even knew what happened. Even if your body could somehow survive, there's another problem: collisions. Space isn't perfectly empty. There are hydrogen atoms scattered throughout interstellar space, about 1 atom per cubic centimeter on average. That doesn't sound like much, but at light speed, those atoms become deadly. When you're traveling at 299,792,458 meters per second, even a single hydrogen atom has tremendous kinetic energy relative to your spacecraft. The impact would be like being hit by a cosmic ray with billions of electron volts of energy. A single atom would punch through your ship like a bullet, and it gets worse. At that speed, even the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, would blue shifted into lethal gamma rays from your perspective. The universe itself would become a radiation furnace, bombarding you with high-energy photons from every direction. Your spacecraft would need shielding so massive and so advanced that it's hard to even imagine with current technology. And remember, adding shielding adds mass, which makes reaching light speed even more impossible. It's problems stacked on top of problems. But here's where things get truly fascinating. While we can't reach light speed, we can ask what the universe looks like from the perspective of things that do travel at light speed. And that gives us profound insights into the nature of reality. Photons don't experience time, they don't age, they don't change. From the moment of emission to the moment of absorption, zero time passes for them. This means that in a very real sense, photons connect distant parts of the universe in ways that transcend our everyday understanding of space and time. When you look at a star 1,000 light-years away, the photons hitting your eyes left that star 1,000 years ago from Earth's perspective. But from the photon's perspective, the journey was instantaneous. The star and your eye are, in a sense, touching across 1,000 light-years of space through a path of zero duration in time. This gives us a strange and beautiful insight. The light connecting every part of the universe exists outside of time. Every photon from the Big Bang's afterglow, every ray of starlight, every flash of gamma radiation from a distant supernova, they all exist in an eternal present moment. Time, as we experience it, is something that only applies to matter, to things with mass, to particles that travel slower than light. In a way, light is the universe's way of communicating with itself instantaneously across vast distances. It's the cosmic messenger that doesn't experience the journey. And that messenger is governed by rules that seem bizarre to us but are actually the most fundamental description of how reality works. Einstein's theory of special relativity tells us that nothing can accelerate to light speed, but it doesn't forbid objects from traveling faster than light if they never cross the light speed barrier. These hypothetical particles are called tachyons. Unlike normal matter, tachyons would require infinite energy to slow down to light speed. They'd exist permanently in the faster-than-light realm. As of now, there's no experimental evidence that tachyons exist. They remain purely theoretical. But they're mathematically allowed by relativity under certain conditions, which tells us something interesting. The speed of light barrier works both ways. You can't cross it from below, and if tachyons exist, they can't cross it from above. What would a tachyon experience? Well, the mathematics suggests that tachyons would have imaginary mass, not in the sense of made up, but in the mathematical sense involving the square root of -1. They'd travel backward in time from certain reference frames. Causality would become even more scrambled. Frankly, the physics becomes so strange and paradox-laden that most scientists doubt tachyons are real. But the fact that we can even ask these questions shows how profoundly relativity has changed our understanding of the universe. Before Einstein, time was absolute, space was absolute, and the idea that they could bend, stretch, and interweave was unthinkable. Now we know better. Let's zoom out for a moment and talk about the expanding universe. Here's something that surprises a lot of people. Space itself can expand faster than light. In fact, it does. Right now, there are galaxies moving away from us at speeds exceeding the speed of light. Wait, didn't we just say nothing can travel faster than light? That's true. Nothing can move through space faster than light. But space itself isn't moving through anything. It's expanding, creating new distance between galaxies. And there's no speed limit on that expansion. The most distant galaxies we can observe are currently receding from us at several times the speed of light due to the expansion of space. This is why the observable universe has a horizon. Beyond a certain distance, currently about 46.5 billion light-years, galaxies are moving away so fast that their light will never reach us. Not because the light is traveling slowly, but because space is expanding faster than the light can cross it. This creates a strange situation. There are photons out there in the universe racing toward Earth at the speed of light that will never arrive. They're on a cosmic treadmill running at maximum speed, but losing ground to the expansion of space itself. Those photons will travel for eternity without ever reaching their destination. Think about what that means for the universe's ultimate fate. As space continues to expand and the expansion accelerates, driven by something we call dark energy, more and more of the universe will slip beyond our cosmic horizon. Future civilizations, trillions of years from now, will look up at the night sky and see far fewer galaxies than we do. Eventually, only our local group of galaxies will remain visible. The rest of the universe will have expanded beyond the reachable horizon. Those future astronomers might never know that the universe is bigger than what they can see. They might develop entirely different cosmological theories based on the limited evidence available to them. It's humbling to realize that we too might be missing crucial information about the universe simply because it's expanded beyond our ability to observe it. But back to our original question, what happens if we reach light speed? We've established that you can't. But understanding why you can't teaches us something profound about the architecture of reality. The speed of light isn't arbitrary, it's baked into the fundamental equations that govern electromagnetism, space, time, and causality. When James Clerk Maxwell unified electricity and magnetism in the 1860s, his equations predicted that electromagnetic waves would travel at a specific speed determined by fundamental constants of nature. When he calculated that speed, it turned out to be exactly the known speed of light. This was one of the great aha moments in physics, the realization that light is an electromagnetic wave. Maxwell's equations don't care about your reference frame. They give the same speed of light whether you're standing still or racing through space. This constancy of the speed of light is what forced Einstein to reconsider the nature of space and time. If light always travels at the same speed regardless of the observer's motion, then time and space must be flexible to make that possible. The implications ripple through all of physics. Special relativity led to general relativity, Einstein's theory of gravity, which describes how mass and energy curve space-time. Those curves tell matter how to move, and moving matter tells space-time how to curve. It's a beautiful feedback loop that explains everything, from the orbit of Mercury to the behavior of black holes to the expansion of the universe itself. And it all comes back to that fundamental speed limit, 299,792,458 meters per second. Not just the speed of light, but the speed of causality, the speed at which information can propagate through the universe, the cosmic speed limit that keeps reality coherent and logical. Here's something else worth considering. While we can't accelerate to light speed, we can use time dilation to our advantage. If you traveled at 99.99% the speed of light, you could cross vast distances in your lifetime as you experience it. Imagine boarding a spacecraft capable of sustained acceleration at one Earth gravity, comfortable for human passengers. You accelerate continuously for the first half of your journey, then flip around and decelerate for the second half. From your perspective, the journey feels relatively short due to time dilation. You could reach Alpha Centauri in about 3.5 years of ship time. The center of our galaxy, about 20 years of ship time. Even the Andromeda Galaxy, 2.5 million light-years away, would take only about 28 years from your perspective if you could maintain that acceleration. But here's the catch. While you're experiencing those years, centuries, millennia, or even millions of years are passing back on Earth. You'd return to a world utterly transformed, if humanity still existed at all. Everyone you knew would be long dead. Civilizations would have risen and fallen. The Earth itself might be unrecognizable. This is sometimes called the twin paradox, though it's not really a paradox once you understand relativity. Imagine twins. One stays on Earth, the other travels at near light speed to a distant star and back. When they reunite, the traveling twin has aged only a few years, while the Earthbound twin has aged decades or even centuries. It's not symmetrical because the traveling twin experienced acceleration and deceleration, changing reference frames, while the Earth twin remained in a single, inertial frame. This has been confirmed experimentally countless times. Muons created in Earth's upper atmosphere by cosmic rays should decay before reaching the surface based on their known half-life. But because they're traveling at relativistic speeds, significant fractions of light speed, time dilation extends their lifespan from our perspective. We detect far more muons at sea level than we should if time flowed the same for them as it does for us. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.999991% the speed of light. At those speeds, the protons experience extreme time dilation. From the proton's perspective, it zips around the 27-kilometer ring in a tiny fraction of the time we measure. The accelerator's designers must account for relativistic effects, or the machine simply wouldn't work. This isn't theoretical physics reserved for textbooks, it's engineering reality. The GPS satellites orbiting Earth experience both special relativistic effects because they're moving relative to us, and general relativistic effects because they're in a weaker gravitational field than we are on the surface. Combined, these effects cause their clocks to run at a different rate than clocks on Earth. Without correcting for relativity, GPS would accumulate errors of about 10 kilometers per day. Your phone's navigation would be useless. The fact that GPS works is constant, everyday proof that Einstein was right about the nature of space, time, and the speed of light. Now let's talk about something truly wild: black holes. These cosmic monsters have a relationship with light speed that's absolutely fascinating. A black hole's defining feature is its event horizon, the boundary beyond which escape velocity exceeds the speed of light. Inside the event horizon, not even light can escape. Space itself is falling into the black hole faster than light can travel through it. This creates a one-way membrane in space-time. Cross it, and there's no coming back, not because you lack a powerful enough rocket, but because every direction in space points inward toward the singularity. The future becomes a direction in space, pulling you inevitably toward the center. From the perspective of someone falling into a black hole, something fascinating happens. As you cross the event horizon, you don't notice anything special locally. There's no wall, no barrier, no sudden change. You just keep falling. But to an outside observer watching you fall, something very different happens. As you approach the event horizon, time dilation becomes extreme. To the distant observer, you appear to slow down, dimming and redshifting as time for you grinds to a near halt relative to them. Mathematically, you never quite cross the horizon from their perspective. You approach it asymptotically, taking infinite time to reach it. But from your perspective, you cross quickly and smoothly. And once you're inside, the laws of physics as we understand them start to break down near the singularity. We don't know what happens at the very center because our equations produce infinities, which usually means we're missing something fundamental about how physics works at those extreme conditions. This is where quantum mechanics and general relativity collide. Relativity describes gravity and the large-scale structure of space-time beautifully. Quantum mechanics describes the behavior of particles and fields at tiny scales with incredible precision. But the two theories are mathematically incompatible. At the singularity of a black hole, where both gravitational effects and quantum effects should be important, we need a theory of quantum gravity to make predictions. We don't have one yet. String theory, loop quantum gravity, and other approaches are attempting to bridge this gap, but we're not there yet. The speed of light sits at the intersection of these mysteries. It's a fundamental constant in both theories, but it plays different roles. In relativity, it's the ultimate speed limit and the conversion factor between space and time. In quantum mechanics, it appears in equations describing how particles and fields interact and propagate. There's a deeper connection too. The speed of light is related to the fundamental structure of space-time itself. In natural units that physicists sometimes use, the speed of light is simply 1. Space and time have the same dimensions. A light year isn't just a distance, it's equally a time. The speed of light is the conversion factor that reveals space and time as two aspects of the same thing, space-time. This unity is profound. It tells us that the universe doesn't just happen in space over time. Space and time are a unified stage, a four-dimensional fabric that can be bent, stretched, and curved by matter and energy. And the speed of light is the fundamental constant that stitches it all together. When we ask what happens if you reach light speed, we're really asking what happens at the boundary between possible and impossible, between the physical and the mathematical, between the universe as we experience it and the deeper reality underneath. The answer physics gives us is clear. You cannot reach light speed if you have mass. But in exploring why, we've uncovered something far more valuable than a simple prohibition. We've discovered that the universe has an elegant, interconnected structure where space, time, energy, mass, and causality are all bound together by fundamental relationships. Let's consider another mind-bending consequence of relativity: the relativity of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different velocity. This isn't just a matter of perception or measurement error. It's a fundamental feature of reality. Imagine two lightning bolts strike opposite ends of a moving train at the same moment according to someone standing on the platform. But to a passenger on the train moving toward one strike and away from the other, the two strikes don't happen simultaneously. The light from the forward strike reaches them first, and in their reference frame, that strike actually happened first. Who's right? Both are. There's no absolute universal now that spans the universe. Simultaneity is relative, dependent on your reference frame. This seems bizarre, but it's a necessary consequence of the speed of light being constant for all observers. As you approach light speed, this effect becomes extreme. Events that are years apart in one reference frame can become simultaneous in another. The faster you go, the more severely the ordering of distant events can change. At light speed itself, the concept of before and after for spatially separated events becomes completely undefined. This is another way of understanding why light speed travel is impossible. It would destroy the coherent causal structure of the universe. Effects could precede causes. Information could flow backward in time. The logical consistency of reality would unravel. But light itself doesn't have these problems because photons don't carry information from their own perspective. They don't have a perspective. They're the medium through which information travels between things that do have perspectives, things with mass, things that experience time. There's something poetic about this. Light is the messenger between the time-bound, carrying information from past to future, but existing itself in an eternal present. It's the cosmic postal service that delivers letters but doesn't read them. Now let's talk about the experiments that have tested these ideas. One of the most famous is the Michelson-Morley experiment from 1887. At the time, physicists believed light traveled through a medium called the luminiferous ether, just as sound travels through air. They reasoned that Earth's motion through this ether should create a detectable ether wind that would affect the speed of light in different directions. Albert Michelson and Edward Morley designed an incredibly precise interferometer to measure this effect. They split a beam of light, sent the two beams perpendicular paths, bounced them off mirrors, and recombined them. If the speed of light varied depending on direction due to the ether wind, the beams would fall slightly out of phase, creating an interference pattern. They found nothing. No matter which direction they pointed the apparatus, No matter what time of day or year, light traveled at the same speed. The experiment was repeated with increasing precision over the following decades. The result was always the same. The speed of light is constant, regardless of the motion of the source or the observer. This null result was initially baffling. It suggested that either the ether didn't exist or Earth was somehow always stationary in it, which seemed absurd. The solution came from Einstein, who boldly proposed that the speed of light is simply constant in all reference frames, period. No ether needed. This single postulate, combined with the principle of relativity, that the laws of physics are the same in all inertial reference frames, led Einstein to derive all of special relativity. Time dilation, length contraction, mass-energy equivalence, the relativity of simultaneity, all of it follows mathematically from those two simple starting points. It's one of the most elegant theoretical frameworks in all of science. From minimal assumptions, an entire structure of profound consequences emerges, and every single one has been experimentally verified. Another crucial experiment involved atomic clocks on airplanes. In 1971, Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners, some traveling eastward with Earth's rotation, others westward against it. When they compared the traveling clocks to reference clocks that stayed on the ground, they found exactly the time differences predicted by relativity. The eastward traveling clocks lost time relative to the ground clocks. The westward traveling clocks gained time. The differences were tiny, measured in nanoseconds, but precisely matched theoretical predictions accounting for both special relativistic velocity effects and general relativistic gravitational effects. More recently, experiments have pushed particles to astonishing fractions of light speed and measured the effects with incredible precision. The Large Hadron Collider accelerates protons to 99.999991% the speed of light. That's 7 nines after the decimal point. At those speeds, the proton's kinetic energy is enormous, and their effective mass increases by a factor of over 7,000. When these protons collide, the energy released can briefly recreate conditions similar to those that existed microseconds after the Big Bang. The particles produced in these collisions, many of which haven't existed in the universe for billions of years, behave exactly as relativity predicts. The theory works even at these extreme energy scales. All of this experimental evidence points to the same conclusion. The speed of light is not just fast, it's fundamental. It's woven into the basic structure of reality at the deepest level we can currently probe. But what about other methods of traveling faster than light? Not by accelerating through space, but by bending space itself. This is where general relativity opens up some fascinating, if highly speculative, possibilities. Einstein's field equations, which describe how matter and energy curve space-time, allow for some exotic solutions. One of the most famous is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. The concept is straight out of science fiction, but the mathematics is grounded in real general relativity. The idea is this: instead of moving through space, you compress space in front of your spacecraft and expand it behind you. You create a warp bubble where space itself moves, carrying the spacecraft along with it. Inside the bubble, you're not moving at all relative to the local space around you, so you never violate the light speed limit. But the bubble itself can move faster than light, taking you along for the ride. It's a brilliant loophole. You're not traveling faster than light through space. Space itself is moving, and you're just sitting in a bubble riding the wave. From the outside, you'd appear to arrive at your destination faster than a light beam traveling the normal route, but you never locally exceeded the speed of light. So what's the catch? There are several, and they're enormous. First, the Alcubierre drive requires negative energy density, essentially exotic matter with negative mass. We've never observed anything like this in nature. Quantum field theory does predict some phenomena involving negative energy density on extremely small scales, like the Casimir effect, but scaling that up to warp drive levels is pure speculation. We don't know if it's possible, and most physicists suspect it isn't. Second, even if exotic matter exists, you'd need vast quantities of it. Early estimates suggested you'd need more negative energy than the total positive energy in the observable universe. Later refinements of the concept reduced this requirement somewhat, but it's still an absurdly large amount, far beyond anything we could imagine producing with any conceivable technology. Third, there are causality problems. If you can use a warp drive to travel faster than light in one direction, someone in a different reference frame could use it to travel backward in time. Combine two warp drives moving in different directions at different velocities, and you can create closed time-like curves, paths through space-time that loop back on themselves, allowing you to arrive before you left. This opens up all the classic time travel paradoxes. Could you go back and prevent your own departure? What happens to causality when effects can precede their causes? These aren't just philosophical puzzles, they suggest that something in the laws of physics must prevent these scenarios, possibly by forbidding the exotic matter needed for warp drives in the first place. There's a principle in physics called the chronology protection conjecture, proposed by Stephen Hawking. It essentially states that the laws of physics must somehow prevent time travel and the associated paradoxes, even if we can't yet prove exactly how. Warp drives might be one of the things ruled out by whatever mechanism enforces chronology protection. Another speculative faster-than-light concept involves wormholes, shortcuts through space-time connecting distant regions. If you could create a stable wormhole, you might step through and emerge light years away instantaneously, effectively traveling faster than light, taking the normal route through space. Wormholes are permitted by the mathematics of general relativity. The equations don't forbid them, but once again, keeping them open and stable requires exotic matter with negative energy density. Without it, the wormhole would collapse before anything could pass through. There's also the problem of creating one in the first place. You'd need to manipulate space-time on enormous scales with incredible precision. Some theories suggest that microscopic wormholes might spontaneously form and dissolve at the quantum level, the so-called quantum foam of space-time, but scaling that up to usable size seems impossibly difficult. And even if you could create a traversable wormhole, you run into causality issues again. By moving one end of the wormhole at high velocity while keeping the other stationary, you could exploit time dilation effects to turn the wormhole into a time machine, creating the same paradoxes as before. The universe seems determined to prevent faster-than-light travel, not just through the straightforward impossibility of reaching light speed, but through multiple layers of obstacles. Every loophole leads to either impossible requirements, causality violations, or both. It's almost as if the laws of physics are conspiring to maintain a coherent, causal structure to the universe. And maybe that's exactly what they're doing. Maybe causality is so fundamental that the laws of physics must necessarily prevent anything that would violate it, even things that seem mathematically possible in isolation. This brings us to a profound question. Are the laws of physics the way they are because they're the only self-consistent possibility? Could the universe work differently, or would any other set of rules lead to logical contradictions that make reality impossible? We don't know the answer. We have one universe to study, with one set of physical laws. We can imagine variations, different values for fundamental constants, different relationships between forces, but we can't run the experiment to see what would happen. Some physicists speculate about the multiverse, where different regions of reality might have different laws of physics. In most of these regions, conditions might be incompatible with structures like stars, planets, and life. We exist in this particular region because its laws allow complexity to emerge. This is called the anthropic principle. We observe these particular laws because we couldn't exist to observe any others. But that's speculative metaphysics. What we know for certain is that in our universe, with our laws of physics, the speed of light is absolute, constant, and unreachable for anything with mass. Let's return to something more concrete, the practical question of interstellar travel. Even if we can't reach or exceed light speed, we can still ask whether meaningful space travel is possible at sublight velocities. The answer is probably, but it would require enormous technological advances and rethinking our relationship with time and distance. A journey to even the nearest star would take years, decades, or centuries, depending on the speed achieved. Generation ships, massive spacecraft carrying entire communities that would live, reproduce, and die during the journey, are one proposed solution. The travelers who arrive at the destination would be descendants of those who departed, possibly many generations removed. This raises profound social, psychological, and ethical questions that go far beyond engineering. Another possibility is suspended animation or cryogenic preservation. If we could safely put humans into a state of deep hibernation for decades or centuries, the subjective experience of the journey could be shortened dramatically. Wake up at the destination as if little time has passed, even though decades elapsed in the outside world. We're nowhere near this technology yet, but research into induced hibernation, states and cryopreservation continues. Some animals can survive being frozen and revived. Whether this could ever work for humans, with our complex brains and delicate biology, remains an open question. Then there's the idea of sending not humans, but information. If we could fully map a human brain and transmit that information at light speed to a distant location, then reconstruct the person there, we'd achieve a form of faster-than-light travel from the subjective perspective of the traveler. You'd close your eyes on Earth and open them on a distant planet moments later, from your viewpoint. Of course, this raises philosophical questions about identity and consciousness. Is the reconstructed person really you, or a copy? If the original is destroyed in the scanning process, does that make it more real? These are the kinds of questions that have haunted philosophy for millennia, now given new urgency by technological possibilities. But now, all of this remains firmly in the realm of speculation and science fiction. Our actual space travel capabilities are vastly more limited. The fastest human-made object ever built is the Parker Solar Probe, which has reached speeds of about 430,000 miles per hour relative to the Sun during its close approaches. That sounds impressive until you realize it's only about 0.064% the speed of light. At that speed, reaching Alpha Centauri would take over 42,000 years. The spacecraft would need to carry fuel for deceleration, or it would just fly past its destination, unable to stop. And it would need to survive the journey through interstellar space, radiation, micrometeorite impacts, equipment failures, and the gradual breakdown of materials over geological timescales. The Voyager probes, launched in 1977, are humanity's most distant ambassadors now traveling through interstellar space. Voyager 1 is about 14.5 billion miles from Earth as of 2026, and it's moving at about 38,000 miles per hour relative to the Sun. At this speed, it would take about 75,000 years to travel the distance to Alpha Centauri if it were headed in that direction, which it isn't. These probes carry golden records, messages from humanity encoded on gold-plated copper discs containing sounds and images from Earth. They're traveling slower than light, bound by the same cosmic speed limit as everything else with mass, carrying information that will drift through the galaxy for billions of years, long after human civilization has either transcended to something unrecognizable or vanished entirely. There's something melancholic about this. Our messages to the cosmos are limited by the speed of light. Any reply would take years, centuries, or millennia to arrive. A conversation with a civilization around another star would be impossibly slow, each exchange separated by years of waiting. This is true even for robotic exploration. When we send commands to a Mars rover, there's a delay of between 3 and 22 minutes each way, depending on the relative positions of Earth and Mars. For a probe near Jupiter, it's 45 minutes each way. For Voyager 1 in interstellar space, signals take over 21 hours to reach the spacecraft. Imagine trying to control a rover on a planet orbiting Alpha Centauri. You send a command, turn left. 4.4 years later, the command arrives. The rover turns left and sends back confirmation. 4.4 years later, you receive it. 8.8 years for a single command and response cycle. Autonomous systems are essential. This light speed delay fundamentally shapes the nature of any future interstellar civilization. Real-time communication across star systems is impossible. Each solar system would necessarily be autonomous, connected to others only by information delayed by years or centuries. If humanity ever spreads to the stars, we'll fragment into isolated communities evolving separately, connected by slow information exchange. Over thousands of years, these communities might diverge radically. Different languages, cultures, perhaps even different biology, if genetic engineering becomes advanced enough. The speed of light doesn't just limit our travel, it limits the coherence of any widespread civilization. An interstellar empire governing multiple star systems in real time is physically impossible. The light speed lag makes it unworkable. Any such civilization would have to be a loose confederation of autonomous systems at best. This has profound implications for the Fermi paradox, the question of why, if intelligent life is common in the universe, we haven't detected any signs of it. One possible answer is that the light speed barrier makes interstellar expansion so slow and difficult that even ancient civilizations haven't spread very far. Even if a civilization achieves significant fractions of light speed, colonizing a galaxy the size of the Milky Way would take millions of years, and each colony would necessarily become independent, culturally and perhaps evolutionarily diverging from its parent civilization. The original species might be unrecognizable after a million years of separate development across thousands of star systems. Perhaps there are thousands of civilizations in the galaxy, but they're all limited by the same light speed constraints we are. They're not visiting us because interstellar travel is simply too difficult, too slow, too expensive in terms of energy and resources. They're staying home, exploring their own solar systems, sending radio signals, and waiting patiently for replies that take decades or centuries to arrive. Or perhaps intelligence is genuinely rare. Perhaps the combination of factors that led to technological civilization on Earth, stable star, rocky planet in the habitable zone, large moon to stabilize rotation, Jupiter to sweep up asteroids, plate tectonics, the particular sequence of evolutionary developments, is so improbable that we're alone in the observable universe. We don't know. The speed of light limits not just our ability to travel and communicate, but also our ability to answer these fundamental questions about our place in the cosmos. Let's zoom out even further and consider the speed of light in the context of the entire universe. Light from the most distant observable objects has been traveling toward us for over 13 billion years, crossing incomprehensible distances to reach our telescopes. We're literally looking back in time when we observe distant galaxies, seeing them as they were billions of years ago. The observable universe has a radius of about 46.5 billion light-years. Wait, how is that possible if the universe is only 13.8 billion years old? Shouldn't the radius be 13.8 billion light-years at most? This apparent paradox resolves when you remember that space itself has been expanding during the time that light has been traveling toward us. A galaxy that emitted light 13 billion years ago wasn't 13 billion light-years away. When it emitted that light, it was much closer. But during the 13 billion years the light has been traveling, space has expanded, carrying that galaxy far away from us. By now, that galaxy is about 46 billion light-years distant. Here's something even stranger. There are galaxies beyond our observable horizon that are receding from us faster than light. Not because they're moving through space faster than light, that's still impossible, but because the space between us and them is expanding so rapidly that the cumulative effect exceeds the speed of light. Light from these galaxies will never reach us, ever. They're beyond what's called the cosmological event horizon, permanently causally disconnected from us. As the universe continues to expand and the expansion accelerates due to dark energy, more and more galaxies will slip beyond this horizon, disappearing from view forever. In the far future, trillions of years from now, hypothetical civilizations arising in galaxies that remain gravitationally bound to each other will look out at the night sky and see nothing. The expansion of space will have carried all other galaxies so far away that their light can never reach these future observers. They'll think they live in an island universe, alone in an infinite void. They'll have no way to discover the Big Bang, no cosmic microwave background to detect, no redshifted galaxies to measure. The evidence of the universe's origin and expansion will have vanished beyond the horizon. This is a humbling thought. We happen to exist at a time when the universe's history is still observable. We're cosmologically privileged in this way. The speed of light, combined with the expansion of space, creates these horizons. It sets boundaries on what we can observe, what we can influence, and what can influence us. There are events in the universe that we will never see, that can never affect us in any way because they're separated from us by more space-time than light can cross. This gets even more mind-bending when you consider the ultimate fate of the universe. Current observations suggest the expansion is accelerating, driven by dark energy, a mysterious component that makes up about 68% of the universe's total energy density. If this continues, the universe will expand forever, growing ever colder, darker, and more diffuse. Eventually, in the unimaginably distant future, we're talking 10 to the 100th power years and beyond, even atoms might decay, black holes might evaporate through Hawking radiation, and the universe might approach a state of maximum entropy, where nothing interesting can happen anymore. This is called heat death, and the speed of light plays a role here too. As the universe expands, information and energy become ever more diluted. The fundamental speed limit means that gathering resources from an ever-expanding volume of space becomes increasingly difficult. Civilizations, if any survive, would be fighting an endless battle against entropy, trying to extract useful energy from an increasingly uniform, low-energy environment. The speed of light guarantees that this battle is ultimately unwinnable. You can't extract information or energy faster than light can carry it to you, and in an expanding universe, the regions you can access are shrinking in cosmological terms, even as they expand in physical terms. But let's return to more immediate timescales and consider quantum mechanics, where the speed of light appears in some very strange contexts. In quantum field theory, the speed of light is intimately connected to the structure of causality and the behavior of particles and fields. One of the weirdest phenomena is quantum entanglement. When two particles are entangled, measuring a property of one instantaneously affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance and was deeply troubled by it. Here's the weird part. The correlation between entangled particles appears to be instantaneous. Measure the spin of one electron and its entangled partner immediately has the opposite spin, even if it's on the other side of the galaxy. This seems to violate the light speed limit for information transfer. But, and this is crucial, it doesn't. You can't use entanglement to send information faster than light. The measurement outcomes are random from the perspective of each observer. You only see the correlation when you compare results with the other observer, and that comparison requires a classical communication channel that's limited to light speed. Entanglement creates correlations that seem to transcend space, but you can't control or exploit those correlations to send a message. Nature is subtle. It allows these spooky quantum connections while still preserving the fundamental causality structure enforced by the light speed limit. This has been tested experimentally many times. The most definitive tests are called Bell inequality experiments, which close various potential loopholes and confirm that quantum entanglement is real, non-local in a certain sense, but still doesn't allow faster-than-light communication. The speed of light remains inviolate even in the quantum realm, but the way it constrains causality is more subtle than you might think. Quantum mechanics is deeply weird, but it respects the fundamental structure of space-time that relativity describes. Another quantum phenomenon involving light speed is the Heisenberg uncertainty principle. There's a deep relationship between the position-momentum uncertainty and the time-energy uncertainty, and both are connected to the fundamental constants of nature, including the speed of light. The uncertainty principle tells us there are limits to how precisely we can know certain pairs of properties simultaneously. This isn't a measurement problem or a limitation of our instruments, it's a fundamental feature of reality. Particles don't have precise positions and momenta simultaneously. They exist in a kind of fuzzy quantum state until measured. This fuzziness has implications for the vacuum itself. What we think of as empty space is actually seething with virtual particles, particle-antiparticle pairs that spontaneously pop into existence and annihilate each other on timescales so short that the uncertainty principle allows them to borrow energy from the vacuum temporarily. These virtual particles are constrained by the speed of light too. They can't propagate faster than light, and their fleeting existence is governed by relationships involving the Planck constant, the speed of light, and the energies involved. The structure of the quantum vacuum, the behavior of fields and particles, the propagation of forces, all of this is intimately connected to the speed of light as a fundamental constant woven into the mathematical fabric of quantum field theory. So where does all this leave us? We started with a simple question. Why can't we reach the speed of light? The answer has taken us on a journey through the deepest structures of reality, space, time, energy, mass, causality, and the fundamental architecture of the universe itself. The speed of light isn't just a speed limit, it's a conversion factor between space and time, a cosmic constant that defines the relationship between energy and mass, a maximum rate of information transfer, and a guardian of causality. It's woven into every equation of modern physics, from special relativity to quantum field theory to the standard model of particle physics. You cannot reach light speed because doing so would require infinite energy, would compress your experience of time to zero, would make your mass infinite, and would break the causal structure of the universe. The closer you get, the more these effects intensify, creating a barrier that's not just technological, but fundamental. Every attempt to find a loophole, warp drives, wormholes, quantum tricks, runs into either impossible requirements or causality violations. The universe seems determined to maintain a coherent structure where causes precede effects, and information has a maximum speed. This has profound implications for everything from particle physics to cosmology, from the search for extraterrestrial intelligence to the ultimate fate of the universe. We live in a cosmos where certain regions are forever beyond our reach, where interstellar civilizations would necessarily fragment into isolated communities, and where the evidence of cosmic history is slowly disappearing beyond an ever-receding horizon. But there's beauty in these constraints. The same laws that prevent faster-than-light travel also give us stable atoms, coherent chemistry, and the possibility of complex structures like stars, planets, and life. The speed of light isn't just a barrier, it's part of the foundation that makes existence possible. We've discovered that asking why can't we reach light speed is really asking why does the universe have the structure it does? And while we can describe that structure with extraordinary precision, map its implications and test its predictions, the ultimate question of why these laws and not others remains open. Perhaps someday we'll understand whether the laws of physics could be different, whether our universe is one of many with varying rules, or whether this particular set of relationships is the only self-consistent possibility. For now, we have one universe to study, and its fundamental constant of nature is approximately 299,792,458 meters per second. That's not just the speed of light. It's the speed of causality, the speed of information, the maximum rate at which change can propagate through the cosmos. It's the speed at which electromagnetic fields propagate, which means it's the speed at which you see, the speed at which your neurons fire. In terms of the electromagnetic interactions governing them, the speed at which every force except gravity operates. Gravity might also propagate at light speed. We detected gravitational waves in 2015, ripples in space-time traveling at precisely the speed predicted by general relativity, providing yet another confirmation that this constant is truly fundamental. The universe is a strange and beautiful place, governed by laws that seem arbitrary until you examine them closely and discover deep interconnections. The speed of light is one of the most profound of these constants, a number that appears simple but contains within it the entire structure of space-time. We may never travel faster than light. We may be forever confined to the snail's pace of subluminal travel, taking centuries or millennia to cross the distances between stars. But in discovering why this limit exists, we've uncovered some of the deepest truths about reality. We've learned that space and time are not separate, that mass and energy are equivalent, that simultaneity is relative, and that causality has a structure enforced by fundamental laws. We've built technologies that rely on these principles: GPS satellites, correcting for relativistic time dilation, particle accelerators, reaching unprecedented energies, astronomical observations looking billions of years into the past. The speed of light has gone from a curious measurement to the cornerstone of our understanding of the cosmos. It's a limit, yes, but also a window into the nature of reality itself. So when you wonder why we can't reach light speed, remember, you're not just asking about engineering challenges or energy requirements, you're asking about the deepest structure of space, time, and causality. You're asking why the universe is the way it is. And while we may never be able to break this barrier, the very act of understanding why it exists has revealed a cosmos far stranger, more beautiful, and more elegant than we ever imagined. The speed of light is absolute, it's unreachable, and it's one of the most important numbers in the universe. If you found this exploration fascinating and want to dive deeper into the cosmic implications of light speed, check out the video on the screen. This is why no civilization could ever spread across the galaxy. It explores these mind-bending concepts with stunning visuals and takes you even further into the challenges and paradoxes of interstellar expansion. You won't want to miss it.